Well, a warm welcome indeed to everyone joining. Thank you for being here. Glad you could make it. Get yourself ready with a notebook, a pencil, or a pen. Whatever you choose to write with is fine. This is math from the void. Math coming at you pretty much out of nowhere. And today we have an interesting problem involving logarithms. We're going to be using some past understanding of piecewise functions, as well as our understanding of logarithms, their properties, and internally there's some rational function and rational expression properties that we're going to discuss as well. So what are some of the goals in this problem? Well, we want to figure out where this piecewise function should be defined, or rather where the pieces of this piecewise function should be defined. And finally, what this k value should be so that this function f of x is continuous. Oh, let's increase the size of that a little bit. Now, there could be more than one value. Oh no, there can't. Find the value of k results in the function f of x being continuous. And actually what we should have you do first is to determine the domain of the pieces of function. Okay. So we want to make this continuous. Let's take a look first at this piece, which is going to be represented for most of the function. That's because a logarithm has plenty of values, right? It takes on plenty of values. Let's look a little bit deeper into this logarithm. So if we have log of x squared minus 9 over x minus 3, we can simplify this. Now, you don't want to use the properties of logarithms which have us break up the logs with subtraction, although this is true, that this is the same thing. But that doesn't really help us at all. What we should do is we should simplify the rational expression inside. And this is kind of ideal because we have a difference of squares on top, so we'll be able to factor that as follows. X minus 3, x plus 3, over x minus 3. And we see that x minus 3 cancels, which is good, but it also presents a little secret that we have to be aware of. If we're going to cancel this, we need to make a mention that x cannot equal to 3. What happens when x equals 3? When x equals 3, there is a hole, assuming that x equals 3 isn't already restricted from the domain. That is important. So if x equals 3 would not have been on the graph anyways, then it's not really a problem. Let's move that back. There we go. Well, all that to say that this logarithmic expression, or this logarithmic piece of the piecewise function, really is just the same thing as log of x plus 3. However, we know that x cannot equal 3. So let's rewrite this function a little bit. F of x equals log of x plus 3. I might as well just call it that. And then I can specify that x does not equal, the x does not equal 3. Did I put negative 3 up there? No, I put 3. Good. X is not allowed to equal 3. So this would make kind of a smooth logarithm graph. In fact, let's kind of sketch it. What do we know about these logarithm graphs, though? They have a domain. So we still need to look in here and understand this, that the inside of a logarithm must be strictly greater than 0. So here we get x must be greater than negative 3, That means that x equals -3 is our asymptote location. And the graph is roughly going to look something like this. Oops, it should go through the point -2, 0. And then it's not really clear which values it goes through, because the way that a logarithm grows is with base and exponents and stuff like that. All right, but we know that x is not allowed to equal 3 here either. So once we get to x equals 3, which would be like right here, there's going to be a hole. In fact, I'll redraw this. Goes to there, goes to there. Okay, so we've determined that the logarithmic piece is only when x is greater than -3 and it has to not equal 3, which means that we need a value to fill in the hole at x equals 3. See, those are our domains for each of these pieces. Now let's find out what the y value of that hole is. The way we can find that out is we can take a limit as x goes to 3 of the function, which means we're going to take a limit as x goes to 3 for this piece, log x plus 3. Now I'm not allowed to plug in x equals 3 to the function because the function is undefined at x equals 3. We already know that from the fact that we got this cancellation, right? This is undefined whenever x is 3, because otherwise we're taking log of 0 over 0, and like, what the heck does that even mean, right? It doesn't mean anything. But this clever, tricky little mathematical object called a limit literally means that x does not equal this number. We're just getting really, really close to it. You know, like a little brother that's annoying you and they're putting their fingers in your face and you're just like, dude, stop touching my face. And then they just put their finger like right next to your face and they're like, well, I'm not technically touching it. It's getting really close, right? That's sort of like the limit process. We're getting really close to where you're basically plugging in x equals 3. This is going to be log of 6. So this just found the y location for the hole. That's how high up this hole is. This is at approximately log 6, which I don't know what that is. You can use a calculator for that. If it's base 10, I can tell you for sure that it's going to be some kind of a fraction, right? It's going to be something small. Because 10 to the 1 power would be 10. So we don't get up to the 1 until we're all the way out here at like 10 or something. Anyways, that means that the value of k must be log 6. So the full piecewise function is written out like this. F of x equals log of x plus 3, as long as x does not equal 3. And you can also include this because this is the domain of the logarithm part. X is greater than -3. And log of 6 at that exact point, x equals 3. This gives us the definition of the piecewise function, and that will allow us to fill in the hole that is right there. Okay, and now we have a continuous logarithmic function. Now, because it's continuous just means that there aren't any breaks in it. That doesn't mean that it's defined all the way from -infinity to positive infinity. For example, as you can see, there's the cutoff point at -3. But for the part where the graph would be at, there are no more gaps, no more holes in it. Okay. So I think that's enough blab out of me. Thank you for joining. I'll see you guys next time.